In today's class on functional analysis, we are going to discuss applications of open mapping theorem. Let x and y be Banach spaces and f belongs to BL of x, y. Suppose that for every y in y, the operator equation f of x equal to y has a solution in x. That is, the map f is surjective. Therefore, by open mapping theorem, f is open. Therefore, there exists some gamma greater than 0 such that for every y in y, there is some x in x with f of x is equal to y and norm of x less than or equal to gamma times norm y. That is, the operator equation f of x is equal to y has a solution whose norm is at most gamma times norm y. So this estimate of norm of a solution in terms of norm of the so-called free term of the equation is important in many situations. So this is one of the applications of open mapping theorem. Now we write a note. Let x and y be Banach spaces. E be a dense subset of y and E be a dense subset of y. If a little y belongs to y but y does not belong to E, since E is dense, we can find a sequence yn in E such that yn converges to y. Then we can find a sequence yn in y such that yn converges to y. And we can find a sequence xn in x such that f of xn equal to yn for n equal to 1, 2, etc. So a natural question is whether the sequence xn will converge to the unique element x of x such that f of x equal to y. The answer is yes. So the answer is in affirmative, since for f of x minus xn, this is equal to f of x minus f of xn. So this is y minus yn. By our previous discussion, we have norm of x minus xn is less than or equal to gamma times norm of y minus yn. And you know that y converges to yn, so this tends to 0 as n tends to infinity. Therefore, xn converges to x as n tends to infinity. Hence, the sequence xn can be called an approximate solution of f of x is equal to y. That is, the solution x in x corresponding to y in y depends continuously on y. So this establishes validity of perturbation techniques used in the theory of operator equations. The perturbation techniques consist of changing free term little bit and admitting a small change in the solution. So we can discuss this using a concrete example. We do an example, show that the approximate solution xn of the initial value problem am of t xm prime of t plus etc. plus a1 of t x prime of t plus a0 of t x of t equal to y of t, t belongs to ab, aj belongs to c of ab, and am of t not equal to 0 for every t in ab with initial conditions x of a equal to x prime of a equal to etc. equal to xk prime of a equal to 0, where 0 less than or equal to k less than or equal to m minus 1 converges to exact solution x uniformly on AB, and so does the jth derivative xn j prime, that is xn j prime converges to xj prime for j is equal to 1, 2, etc. m as n tends to infinity. So solution: by existence and uniqueness of solution of ordinary differential equations, for every y in say AB there is a solution to the above differential equation which satisfies the initial conditions, and such a solution is unique if k equal to m minus 1. So let y equal to CAB, x equal to set of all x in CMAB, set of all mth differentiable functions satisfying the initial conditions x of a equal to etc. xm minus 1 prime of a equal to 0. For x in x, let f of x equal to am into x m prime plus etc. plus a1 into derivative of x plus a0 into x. Then f is a function from x to y which is linear and bijective, is linear and bijective. Consider the subnorm on y and let the norm on x be given by norm x equal to subnorm of x plus subnorm of first derivative of x plus etc. plus subnorm of mth derivative of x. Then x and y are Banach spaces and f belongs to BL of xy, since subnorm of f of x is equal to, norm of f of x is am mth derivative of x plus etc. plus a1 x prime plus a naught x. So this is less than or equal to an mth derivative of x subnorm of plus etc. plus subnorm of a1 first derivative of x plus subnorm of a naught x. So this is less than or equal to subnorm of am into subnorm of mth derivative of x plus etc. plus subnorm of a1 into subnorm of first derivative of x plus subnorm of a naught into subnorm of x. And we have norm x is subnorm of x plus subnorm of x prime plus etc. plus subnorm of mth derivative of x. From that you will get this is less than or equal to subnorm of am into norm x, where norm x is subnorm of x plus subnorm of first derivative of x plus etc. plus subnorm of mth derivative of x plus etc. plus subnorm of a1 into subnorm of x norm of x plus subnorm of a naught into norm of x. So that is equal to subnorm of am plus etc. plus subnorm of a1 plus subnorm of a naught into norm of x. That is subnorm of f of x less than or equal to subnorm of am plus etc. plus subnorm of a1 plus subnorm of a naught into norm x. So this is true for x in x. Therefore f is in BL of xy. Let E denote the set of all polynomials on AB. Then by point 1, 2 E is dense in CAB. Suppose that for every P in E we are able to find a unique element x of x such that f of x equal to P. For convenience, you let a equal to 0, b equal to 1. Consider function y on 0, 1 which is not a polynomial. For n equal to 1, 2, etc. let Pn of t equal to sigma k equal to 0 to n y of k by n nck t raised to k into 1 minus t raised to n minus k. So t belongs to 0, 1. Then as in the proof of Theorem 3.12, norm of Pn minus y converges to 0 as n tends to infinity. Now for each n, find xn in x such that am mth derivative of xn plus etc. plus a naught xn equal to Pn. Now since Pn converges to y and y equal to am mth derivative of x plus a m minus 1 m minus 1th derivative of x plus etc. plus a1 x prime plus a naught x, we have the sequence xn in x converges to x in x such that am mth derivative of x plus etc. plus a naught x equal to y. That is mth derivative of xn converges to mth derivative of x etc. Derivative of xn converges to derivative of x, xn converges to x from this observation since Pn converges to y. Therefore, the approximate solution xn of the initial value problem converges to exact solution x in x uniformly on AB. Here it is actually on 0, 1. So this is true for AB. And so does the jth derivative. That is, the jth derivative of xn converges to jth derivative of x for j is equal to 1, 2, etc. m, and as n tends to infinity. So this solves that problem. That's all for today. Have a nice day.